And you're going to tell us about Werner Heisenberg. Why don't you get started, John? I'll work on this.
Okay, so he was born December 5th, 1901, in the city of Würzburg in the Bavaria region, northwest. Or I guess really it's more like central Germany. He was born in what's known as Franconian wine country, area that's known for rich wine, and it's really well known for its culture. Has lavish growth and architecture. We'll get into that in a second. And his father, Dr. August Heisenberg, was a professor at the University of Munich, and he taught Greek literature, and his mother was Anne. And this is just essentially Franconian wine country, as you can see. It's this area right here, and Würzburg is like right there. So it's really well known for its great wine. Just to give you an example of the kind of architecture city he was born, this is some Baroque architecture, and it's late 16th century, and it really focuses on the triumphs of the Catholic Church. Really grand architecture. And then similarly, we have architecture. And this is a little bit later. It's the early 18th century. It was kind of the end of the Baroque period when this became prevalent. And it focuses on light colors and elegant architecture using rock, basically. As you can see, here's some examples. So his early education, he went to Maximilian School in Munich for his school before college. Then he went to the University of Munich under Sommerfeld and a lot of other great scientists. He went to Göttingen to study physics under Max Born and more physicists. And that's where he spent a lot of his education career. So, and then he got his PhD at the University of Munich and was an assistant under Max Born at the University of Göttingen. And that's so what he's really well known for is his help in establishing quantum mechanics. And he did this at the age of 23. From what I found, it basically describes the nature of the smallest scales and energy levels of atoms and subatomic particles. I don't know exactly what that means. I'm not that smart. I'm sure you all do.
You didn't have that in your accounting course?
Yeah, right. Yeah, I did some research on it, but it was a lot of it was over my head. So that was basically the summary. Although Max Planck is known as the father of quantum mechanics, Planck, Heisenberg, and Erwin Schrödinger had equal claim recognition for the theory. And Heisenberg gets special credit for the Heisenberg uncertainty principle, which states that there's a fundamental limit to what one can know about the quantum system. I think it's you can never know how fast something is moving and know its expectation at the same time.
For small system. Of course, you have a big system, automobile, you know both. But when you go to the atomic level, small level, you can't know both.
And that's a picture of so he worked with a Rockefeller grant with Niels Bohr at the University of Copenhagen. A lot of time in Copenhagen. And that's a picture of Niels Bohr. 1926, he was appointed lecturer in physics at the University of Copenhagen, still under Niels Bohr. In 1927, he's still only at the age of 26, so he's still almost very young. He was appointed professor of theoretical physics at Leipzig. In 1929, he went on a tour of the world, lecturing in the United States and in India. World War II starts in 1931. I'm not really going to get into what happened there because I think that's really his own PowerPoint itself. So I just kind of focus on his career. And right after World War II starts, he is awarded a Nobel Prize for his contribution to quantum mechanics. In 1941, he is appointed professor of physics at the University of Berlin. And a few years after, he was taken prisoner at the end of World War II and sent to England with a few other Nazi scientists. And after World War II, he returned to Germany and reorganized the Institute for Physics at Groningen. I suppose it was damaged in some way due to the war. And soon after, the institute was renamed for Max Planck. It was called in 1953, he became the president of the Alexander von Humboldt Foundation. He got, starting in 1953, he was really concentrated on unified field theory of elementary particles, which basically, what I read was, he was trying to understand the physics of the elementary particles. And from that point on, starting in 1957, he was concerned about plasma physics and thermonuclear processes.
Okay, chapter 14. Oppenheimer. We've talked about him some before. Which one of you is talking about? Okay, so you talked about Oppenheimer. You discussed how he grew up in New York City. His parents were Jewish immigrants from Germany. He was sickly as a boy, a nerd, didn't have friends, and so his parents sent him to New Mexico to toughen him up one summer at this boys' school up on the Mesa, which became Los Alamos. Did his PhD work in Göttingen. He went to Harvard after he got toughened up. Then went to Göttingen to do his PhD. Very diverse guy. Read poetry, spoke languages, learned Sanskrit, and then became a faculty member at Berkeley and became the leading American theoretical physicist. He was arrogant, he was snobbish, he was dismissive of people, especially those that weren't as smart as him, which is most of the population. And he was just he was the best American theoretical physicist, and he showed it because he was just an arrogant kind of guy. He was not a Nobel laureate. Later on, when he was asked to run the Manhattan Project, that was an issue because, we scientists are kind of snooty at times. Right? Yes. And so when Nobel laureates, already Nobel laureates, were going to work on the Manhattan Project, questioned whether this non-laureate was up to the task. He did not read newspapers, did not know what was going on in the world. It took him a couple of years to know that the stock market crashed because he lived in his own world of physics and was not aware of the outside world. But that all started to change. He spent time in Göttingen, of course, for his PhD. Then when Hitler started changing Germany, getting rid of the Jews, and that had a big impact on him. Then also, he saw finally the effects of the recession, of the Depression, when students at Berkeley trying to study physics were not able to support themselves. My granddaughter called her later. She's a college junior at the University of Colorado in Boulder. Where the Chicago these days. I'll talk to him later. He was a ladies' man, Oppenheimer was, a handsome guy and very popular at parties. Not only brought flowers for his date, but also generally brought flowers for the other women at the party. So he was well appreciated. And he, Jean Tatlock was a lady that he dated for some time. And, you know, she was an activist, a member of the Communist Party. For a lot of people in the 30s who were associated some way, sympathetic to the Communist Party. Capitalism wasn't working, just had the depression. And so he's one of those people that flirted with communism. But he read Marx and Lenin and the others, and it didn't make any sense to him, so he did not accept them. He married Kitty Oppenheimer. Kitty was born in Germany, kind of some kind of a noble family. And so she was married 3 times before she married Oppenheimer, married somebody while in Germany, then came to the US, married Joe Gallant, who was a communist, US Communist Party. He then fought in Spain, killed in Spain. Then she married, she went back to school, University of Pennsylvania, to get her degree in botany, smart lady. Then she married a British physician. Then she met Oppenheimer, and she married Oppenheimer on November 1st of 1940, the same day that her divorce from the British physician became final. And so Kitty was a outgoing lady, very active lady, and they were a good pair for a long time. But she also flirted with the Communist Party, was married to a Communist Party official in the US, where he was killed in Spain. That was then something that plagued Oppenheimer throughout his career. It plagued Oppenheimer when Groves chose him to run the Manhattan Project, because the Security Commission said, you can't choose him. He's got communist friends, communist leanings perhaps, not trustworthy. We'll discuss it, he got through that, but then even after World War II, in the McCarthy era in the US, that caught up with him. And he lost his security clearance because of these connections with Kitty, Jean Tatlock, and whatever. And so in 1954, he lost his security clearance, and then his career as a scientist at the highest level of government were done. It was not until 1967 that that he was kind of brought back into the fold. I think we discussed that with Lyndon Johnson, right, Ray? That John Kennedy intended to do that, but he was killed. But he was then kind of resurrected Oppenheimer was before he died. So we talked about Leslie Groves. One of you just talked about Groves. So he was in charge of the Manhattan Project. He was chosen to lead this. He got attacked in December of 1941 at Pearl Harbor by Japan. So by 42, in the summer of 1942, Leslie Groves was appointed to do something with this project, to see if we can build this atomic bomb, gather scientists, build a laboratory or two. Groves first wanted to make Ernst Lawrence the leader of the project. He was the Berkeley physicist, experimental physicist who invented the cyclotron. You know, real hands-on guy who was a good inventor. But he backed off from that because Ernst Lawrence was busy and was crucial for this idea of enriching uranium by electromagnetic separation, take off on his cyclotron concept, for which he got a Nobel Prize. Groves thought about Arthur Compton, the guy from the brother of the president of Harvard, Nobel laureate in his own right. Was in Chicago now running the metallurgical lab, the Met Lab, part of the Manhattan Project. But he was tied up. Thought about Harold Urey, another Nobel laureate. He was a chemist. But it's not good to choose a chemist.
I wouldn't even consider it.
Anyway, so finally Groves apparently hit on Oppenheimer because he was a very smart guy, very quick. And Oppenheimer had gathered in the summer of 42 a group of scientists, physicists, chemists to talk about what an atomic bomb might be. And he did a good job of that. And he was Nobel laureate. Lawrence, Compton, Urey were Nobel laureates. Oppenheimer was not, but still, Groves figured out that he was highly respected, very smart, and would be the best person he could find to lead the Manhattan Project. The security people were dead set against it. These communist connections. Gene Tatlock, Kitty, he married him. And so they were objecting to him greatly, but Groves said, there's nobody else, you gotta let me do this. So he was able to appoint Oppenheimer as head of the Manhattan Project. Oak Ridge, of course, was the original site for the Manhattan Project, Site X. 52,000 acres were designated. Groves and Oppenheimer decided to need another site. It says Site Y there for another place that where you could do design and construction of the actual weapon. You know, the purpose of Oak Ridge, Clinton engineer works was to separate uranium, figure out how to make plutonium in a reactor. You need another laboratory to design and construct the weapon. Groves wanted to put it in western Mississippi. Had to be far from something, had to be 200 miles from the international border, had to have water and a decent climate, and isolated for security purposes. He got to the point somebody to go around and check out sites. The guy that did this, his first choice was Oak City, Utah, right here, but Groves rejected that. The problem was that the airport was too distant, there was not enough, that there was water, that there were hills, it was isolated, but the problem was that you'd have to move quite a few families, and you take good land out of circulation for farming. And that was a problem during the war that was perceived. Second choice was in New Mexico. A canyon, the New Canyon, northwest of Santa Fe. And that was initially one of the requirements by Groves. It has to be in a canyon surrounded by walls so that you can really secure it. Keep it away from spies or terrorists. There was the population there, but it seemed to be a very good place for making the second laboratory, Lab Y. Oppenheimer and Groves visited that place, named as Springs, New Mexico, in November of 42. They felt that the canyon was too confining. It was secure, but the canyon was just too small and too confining. Oppenheimer wanted the site with a view. Oppenheimer had been up on top of the adjacent mesa. That's where his parents had sent him as a teenager to toughen him up. He was sent to the boys' school. He was sent to the Los Alamos Ranch School on top of the mesa adjacent to that canyon that Groves' aide had picked as the site. Oppenheimer wanted that. The vistas were great up on top of this mesa, 7,200-foot mesa. And they figured that could be secure also because it's on top of a mesa and you could well defend that and secure that. This is where Oppenheimer spent time as a teenager at the ranch school, a place to toughen up kids. They slept outside on the porch. Boys did in summer or winter. In November of 42, when Groves and Oppenheimer went there, they saw boys who were there living for a year playing soccer out in the snow in shorts. So it was to toughen up these kids in any way.
That was a requirement. They only had
Only had shirts.
Did not allow for a long.
You'd like to analyze whether those kids got toughened up or went crazy or died of frostbite.
Yeah.
Interesting. So that's what they chose up on top of the mesa, and they were able to utilize the school. They bought the school from Ashley Pond, and that became the site of Laboratory Y. Groves asked the University of California to manage and operate the laboratory, and that was something that existed. Still, the UT Patel runs Oak Ridge National Lab. The University of California has been involved in the management of Los Alamos National Lab ever since 1942. They needed equipment. Oppenheimer convinced people at Harvard to move the cyclotron that they had built there for doing nuclear physics to up on the mesa. They went to the University of Wisconsin where Ray Herb was, and they built 2 linear accelerators called Vandergriff accelerators, and convinced them to move those to Laboratory Y on this mesa. The big job was Oppenheimer then to convince eminent, talented scientists, physicists, chemists, engineers to move to this godforsaken place up on the mesa in the middle of New Mexico. Some people were horrified. Szilard, the Hungarian Jew, was a cosmopolitan guy. He sure as hell didn't want to be there. He was in the middle of nowhere. He was horrified by the choice. Hans Bethe was from Europe, and he became convinced. He was skeptical that this would work. This could work either technically or going to this little place in the middle of nowhere. But Hans Bethe, an eventual Nobel laureate, moved there. Edward Teller, another Hungarian Jew, was not happy in Chicago at the Met Lab, but he moved there willingly. Isidore Rabi was another Nobel laureate, decided that was too remote. The chances of that project to build a bomb was too unlikely, so he decided to stay at MIT and work on radar, which is a crucial step for the war, too. There was debate over how these scientists and engineers and chemists would be accommodated. One idea is they would become officers in the Army. This would be Army-run, this laboratory. Oppenheimer greatly objected to that. He knew that his scientific colleagues would hate that. And so the compromise was that they would remain civilians and that they would be able to speak with each other rather openly about what they're working on in a limited way. So there would be communication with each other, which is the essence of science, to debate what works, what doesn't work, and how to do it better. But the compromise was that there'd be a fence around the laboratory and the city up on the mesa. And if your mother-in-law come visit, she had to get clearance to come to the city, which is Safe Road Bridge. So the security was very heavy. Then to divert about the same time back to the heavy water plant in Norway. Outside of Oslo, 90 miles west of Oslo, was the Vermork, the Mork hydroelectric plant up in the hills. And it was because of all the water in the mountains, it was a hydro plant to make electricity, but also with that electricity, it produced heavy water as a byproduct of making hydrogen. Ammonia. Ammonia is important for making fertilizer. Norway is a big time farming country. And so you need hydrogen to make ammonia, NH3. And so that's why they're making hydrogen at this plant with the abundant electrical power. And heavy water was a byproduct of that. So heavy water had different industrial purposes, but the Germans knew, the Nazis knew that there was a heavy water plant. And so that's why the Nazis went into Scandinavia, took Denmark without resistance, took Norway with some resistance, in part because they needed heavy water for this plant to fuel Heisenberg's direction of trying to build a reactor. Fermi chose graphite as the moderator. Heisenberg, probably because of a mistake by Walter Lotze from Heidelberg, chose heavy water as the needed moderator to make a reactor work in order to make plutonium artificially for their atomic bomb. This was the source of heavy water. British tried to sabotage this. The British with Norwegian participants tried to glide into this area, British sabotage effort, and that didn't work. 19 people tried to glide in to get into this area in order to sabotage this, blow up this plant to disable it as a source of heavy water for the Nazis. But that failed. They were captured. Some died right away. 14 were captured, were executed by the Germans. So that didn't work. This was so important that the British decided to support another sabotage effort. This time they used Norwegians who were native to the area as the lead on this. And they were then trained and they were parachuted to a frozen lake 30 miles northwest of the site in February of 43. The 6 of them teamed up with 4 of this crew who did survive. They've been living there for some weeks in the frozen mountains, barely alive. They needed 10 days to get those 4 back to enough strength that this then group of 10 saboteurs could make another go at sabotaging this heavy water plant outside of Oslo. Then, on the night of February 27th, they're camping on a gorge overlooking the plant. This is the movie, by the way, about this. That's Kirk Douglas. He played a Norwegian physicist. Not very convincing. Did you watch that yet? And this is a movie about the heroes of Telemark. It's about this sabotage effort. So they slid down the gorge of the snow-covered mountains to try and then they cut through a security fence. They got onto the site. The Germans were not guarding this very well. It was a noisy plant, so they couldn't hear people cutting the fence, sliding down the hill through snow and trees. And it was only, the terrain was so bad, they really didn't expect a team of saboteurs coming. Half of the team got into the site after midnight, cut through a chain link fence. That team blew up the 18 cells that were used for making heavy water in that plant. The Germans thought they heard some noise. They thought it was maybe an avalanche set off by a landmine around the plant. And it worked very well. All the 10 Norwegians got off the mountain and were gone before security sirens went off. And that's what that movie's about, the Kirk Douglas movie, about that successful sabotage effort. To jump to Japan, Japanese scientists were also working on ideas about whether you could and how you could build an atomic bomb. So they had a project started in 1941. The Ryukyuan lab in Tokyo was supported by the Army concerning ways to enrich uranium. By the next spring, the spring of 42, the Navy and did commit to trying to develop nuclear energy to power submarines, ships. And 2,000 yen, $4,700 was appropriated for this purpose, for the uranium enrichment project. Not a lot of money, but it was similar to what the U.S. first got when Fermi and Szilard got some money to work on purity of cadmium, testing cadmium for their reactor project. Then they had a series of study sessions the Navy committee did in spring of 43, they decided that it was just too difficult. It would take too much power, electrical power, maybe a tenth of their total electrical power in Japan. It would take too much copper output for windings of electrical coils to do uranium purification and enrichment, like the Green Meadow Bridge. They decided it was they didn't have the resources, and they decided that Germany and the US, they're working on this, did not have the industrial capacity to fight a war and develop all the technology needed to make an atomic bomb. So the Navy dissolved that committee, suggested that Japanese scientists work on radar instead. There was, however, a different arm of the Navy. They weren't communicating with each other very well. They did put significant money into building a cyclotron at Kyoto, which would be important then for learning about plutonium and whether you can make a bomb that way. However, it never went anywhere. That was an isolated effort, that $1.5 million to build that cyclotron, and it never really went anywhere in Japan. In Los Alamos now, Oppenheimer was gathering people, bringing people to this place in New Mexico, not too far from Santa Fe and Albuquerque. It's still very, very isolated. Robert Server was one of his former students at Berkeley, got his PhD working with Oppenheimer. He brought Server there, and he asked Server to develop a series of lectures on fission, on the issues of Palomino bomb. And those have been published, so to speak. Those are the Server lectures. It's called the Los Alamos Primer, written by Robert Server. So as every group of scientists arrived at Los Alamos who knew little about what the goal was, what the technology might be, Server gave lectures, or they handed out these notes, a primer on the nature of nuclear fission, how much energy is, and that's a document that's been declassified from lectures in April 1943 by Robert Server. So that's the Los Alamos Primer that every arriving scientist at high enough level was given to get them up to speed on what this project was. So in this series of lectures, Condon was Oppenheimer's associate director. He wrote the notes in Server's lecture. Server could in a kilogram, but a kilogram of U-235, once you enrich it, is the equivalent to blast potential of 20,000 tons of TNT. Huge weapon. He concluded, based upon calculations, somewhat from that summer study that Oppenheimer had led, that it would be possible for this chain reaction to go fast enough. In other words, as this thing starts to explode, if the next generation of neutrons is given off too slowly, then the blast tears apart the hunk of uranium before it can sustain itself and cause this chain reaction and the release of 20,000 tons of TNT. That was one of the critical questions. How fast is that set of chain reactions? He pointed out, Server did, that on average, this 2.2 neutron per minute fission of U-235, which is a crucial number. That meant you could do a chain reaction. He pointed out that uranium in the ground is not going to fission because uranium-238, most of natural uranium, has this resonance at 25 electron volts, very low energy, that captures a neutron, which, by the way, leads to production of plutonium-239. And he pointed out in these lectures that you had to have a tamper, it's called, around the fissionable uranium or plutonium that would then slow down the expansion. The thing is blowing up, and you have to slow down that dispersal material, the explosion, to keep it compact so the chain reaction can go on and have that huge nuclear event, the atomic bomb, therefore. And so if you didn't have the tamper, you would have fission at only a small amount of material, maybe 1%. So those are a crucial set of guidelines that people are starting to understand. So part of it was the tamper. Something as you drew around the uranium, this is a blackboard sketch, that would be there to keep the uranium compact, and so that it wouldn't expand too fast and allow a chain reaction to go on. And calculation showed you would need 2 critical masses of uranium to make this work, because the expansion, even if the tamper surrounding the uranium slows its expansion down, still you probably need twice the critical mass of uranium to really make a bomb. And then they talked about how to detonate it. Maybe you have 2 critical masses and you shoot them together. That's what this kind of thing is. You shoot a hunk of uranium on the edge of this bullet into perhaps a sphere with a shell of uranium. And once that then is there, that completes critical mass, and the chain reaction goes on. You need something to detonate. You need a source of neutrons, Server pointed out. You need, a few neutrons to get this going, to get this chain reaction started. And that would be perhaps a plutonium-210 right at the source that gives off alpha particles. And then, this is what Marie Curie was doing in Fermi in Rome, and Hahn and Meitner in Berlin. You could get neutrons that way by taking alpha particles from this naturally occurring radioactive material, taking a beryllium foil, that gives a few neutrons, and that would initiate this chain reaction. So the idea is you might have the polonium on this bolt, and the beryllium in this material, and then when you shot them together, voila, you get a few neutrons to then initiate this chain reaction. And that's sketchy. They had to then make all this work. That was to show people arriving what is the status. So there are many problems to solve. The timing. How fast can you shoot the 2 hunks of uranium together to make it work? So a little better view of that crude diagram is that you've got some uranium, you've got tamper around it, you've got shooting into it, you've got some more uranium with tamper. You shoot that together in a conventional gun type of process. And when this is coincident with that chain, then you get the chain reaction. You have that initiator, and then you can have the chain reaction go on. So they understand the hydrodynamics as that all turns to liquid. When you start getting chain reaction, you get a lot of energy. That uranium, that tamper, all becomes liquefied. And so in that process, turning to a liquid, how do the neutrons propagate? How do you build an initiator? How do you make the enriched uranium plutonium into some metal form that you could use then in this voltage mechanism? So that's for the uranium bomb. And the uranium, one bomb drop in panels like that, mechanism to shoot that core into uranium. But that wouldn't work, people realize, as part of the server lectures, for plutonium. So plutonium was a more difficult thing to make fission, to make a bomb out of, because it would start to have spontaneous fission, a different isotope of plutonium. So they realized then that you needed that this slow type of gun mechanism wouldn't work. Seth Niedermeyer was there an engineer or a physicist, he had experience with explosives, with ordnance. And he was viewed as a rebel initially, but he came up with the idea that this mechanism won't work with plutonium. Instead, you need to have implosion, not explosion, you need to have implosion, where in this scheme, you would have some plutonium, you'd have it surrounded by high explosive. And if you made all of those explosives and that spherical array go off rudely simultaneously, then you could compress the non-critical plutonium inside suddenly into a critical mass, and then it would have a chain reaction and explode. And so that was what Niedermeyer proposed. And Oppenheimer initially viewed Niedermeyer as a pain in the butt, somebody who didn't know what he was talking about. So I don't think it'll work, Niedermeyer, but you go and take a group and you see if you can make a uniform implosion. A huge technical challenge. Well, at the same time now you're talking about early 43, the war in Europe is getting worse and worse. The atrocities were getting more and more severe. The Germans started off the air war by the Battle of Britain, doing bombing of London every night for 6 months. Then the Brits responded by attacking Germany, a lot of back and forth. Initially, the air attacks on both sides were precision bombing, which meant the Brits would attack German air bases or munitions factories. Very selective, very precise, only on the military or industrial targets. But you had to do that in the day so that you could see those sites bombed precisely. That was getting to be dangerous because the Brits were losing too many aircraft. And so this evolved to nighttime bombing by the British or by the Germans to avoid losing the aircraft. Well, but if you went to nighttime bombing, then you couldn't see the munitions factory very well. And this then evolved into area bombing instead of precision bombing, where now evolved to the point where you're just bombing cities, not for military purposes, but just for psychological purposes. And that had happened already in 41. You know, Stalin was flying off the German attack on Russia. He needed help on the Western Front. And we weren't ready. England was not ready to invade Europe. And so instead, they replaced precision bombing with area bombing. And then after Pearl Harbor, some of our aircraft came over. And by 42, they're using incendiary bombs on cities, which is a real atrocity also. And the idea here, bombs do not destroy buildings, bombs start fires in cities. And you would then have, use napalm and different white phosphorus and different things, chemicals, that would then set hot fires that would engulf the city and melt everything, kill everything in that area. The Germans first started using incendiary bombs in the Battle of Britain. The Brits attacked Cologne that way. The first big one was summer 43, an attack on Hamburg, Germany, where it's now carpet bombing with incendiary devices where one wave of British aircraft to another laid down these incendiary bombs that just coated the city and had these fires start temperatures of maybe 1,400 degrees due to the citywide massive fire. Of course, everything was on fire. And everything was killed in the process. In Hamburg, 45,000 people were killed those 2 nights by incendiary bombing of the city. Same thing was done in Dresden. Incendiary bombs that just destroyed the city. And so, you know, the atrocities were getting worse. On the Russian front, you know, Hitler captured 1 million soldiers as he was trying to take Moscow, and they were just left to die with no water, no food, in prisoner war camps. So then that led to the next step along the way. It was not in chronological order, but also along the way, the Nazis decided the quote, final solution to the Jewish question, which leaders in Germany debated. The final solution was to exterminate the Jews. The Jews were Germans, but also the Polish Jews, to just exterminate them, not just put them in concentration camps. You know, back in the U.S. now, Los Alamos was functioning, Oak Ridge was functioning, Hanford, Washington was starting to build their reactors, scale up of the Oak Ridge reactor. People were more and more seeing how to build an atomic bomb, and you needed an aircraft to deliver it. And you know, it had to be a large aircraft because the 2 bombs, the uranium bomb and the plutonium bomb, were being constructed for heavy devices. And they were long devices, especially the uranium bomb was a very long device. So the idea was to take a B-29 Super Fortress aircraft, one of the biggest airplanes, military aircraft at that time, and to convert it to have a long bay. You know, it was just right. It had good technology, remote control machine guns, it could fly at high altitudes, but also do involved in low altitude incendiary bombing of German cities. They haven't been tested yet, but people decided Los Alamos this would be the best aircraft. And then, so Norman Ramsey, who became a Nobel laureate at Harvard, is a young physicist there at Los Alamos. He in charge of figuring out how to redesign this so that you could load a heavy gun-type atomic bomb or the spherical plutonium bomb into the bay. And by the way, secrecy was paramount. And so Thin Man and Fat Boy terms were derived at that time. Fat Boy was meant to be Churchill. Thin Man was meant to be Roosevelt. And so when they were talking to each other about designing aircraft for Thin Man or Fat Boy, you would hope the spies would think, well, they're talking about how to carry Roosevelt and Churchill around. Back to Denmark. I alluded to this before. You know, there were 8,000 Jews in Denmark that were left alone for a while. Nazis went into Denmark in 41. A quiet deal was made, and that Germany allowed Denmark to keep functioning. The king was still in charge, Christian X. He rode his horse every day through the streets of Copenhagen throughout the German occupation of Denmark as a sign of silent resistance to the Nazis. The Germans needed the agricultural products from highly efficient Danish farms, especially meat and butter, to feed the homeland. And so the Nazis allowed the monarchy to continue and the Danish Jews to be left alone. However, Danish resistance movement was annoying the Germans, blowing up bridges and trains. In February, the Germans surrendered at Stalingrad. That was the blow. July of 43, Mussolini in Italy resigned and was arrested. August of 43, that it was time to keep us on Germany. Things were not going well, and so it was decided that they declared a state of emergency in Denmark and made resistance illegal. Christian X refused to accept those emergency terms. The troops came back the next day and occupied Denmark again, confined King Christian X. The next step was to take possession of the 8,000 Danish Jews and send them to concentration camps. And Bohr learned about this. There was a plant of the Danish underground working in the Gestapo headquarters, and through that he learned that the Jews would soon be rounded up in Denmark. And so on September 28th of 1943, in that plant in the Gestapo headquarters, he learned that he was about to be arrested. Niels Bohr's mother was Jewish, turns out. And so he was the most visible, besides the king, Niels Bohr was the most visible Dane. And so the next day, Bohr was going to be arrested. Well, he heard the news, he got tipped on that, and so that night, Niels and Margareta were taken across the Öresund, across the sea to Sweden, just to get them over to neutral Sweden. And so to keep them from being arrested by the Gestapo. Now, 74 Niels was dead. I arrived there as a postdoc in fall of '68. Niels had died in '63, so I never met him. Margareta is still alive, so I met her. Got to know her a little bit. The next step, of course, was to round up all the Jews in Denmark. And so Bohr passed the word. Bohr got the King of Sweden to accept taking the Danish Jews if they could get across the Öresund to Sweden. Bohr convinced the King of Sweden to make a public announcement that Sweden would accept the Danish Jews. That then signaled the Danish underground to get 7,220 Danish Jews hidden, like the day before the Gestapo was about to swoop in and arrest them all, hid them in farms and barns throughout the island on which Copenhagen sits, and then over some weeks and months, got them ferried across by private fishing vessels, one by one, to Sweden. All the time avoiding German warships, mines, and all that, and it worked. There were some Jews who were in nursing homes or hospitals that didn't get rescued, but of the 8,000, 7,200 Jews in Denmark got saved by being taken over to Sweden. And so that was the largest successful resistance to the Nazis in World War II. It's a remarkable story. Bohr got to Sweden, went to England. The worry was in Stockholm, there were a lot of German agents and assassins. Sweden was neutral, but it was teeming with German spies and assassins. So we decided the Bohr would be safer in England. And so they had a small 2-engine craft that was going to fly Bohr to England to get them out of, get them in safe quarters. And it was for diplomats and such. The problem was Bohr had a large head. The helmet they gave him for this flight wouldn't fit. And so he was not able to make his oxygen mask work. So he passed out in that flight. Could have died, but survived because he was a strong person physically. But he did it for England, and then the next step was to get into the U.S. to contribute to the Manhattan Project. Ray, do you have anything you want to contribute to this story?
I'll pick a little piece that you mentioned about the change in tactics for the bomb and going to a plutonium-based suppression bomb that had 32 implosions to compress that plutonium. That was a struggle all through the time of them trying to determine how, even if one of them didn't go off simultaneously, you have a blowout, so you wouldn't get the compression that you need. So that was a struggle. That's the main reason for the test at Trinity, was to prove that that process works. Now there's a unique twist that ties the submarine, Nazi submarine U-234, to that implosion bomb. The Nazi submarine U-234, which surrendered to American forces in May of 1945, was found to be carrying a surprisingly diverse cargo bound for Tokyo as a part of a secretive exchange of war material between Hitler and the Emperor Hirohito. The payload presented the pride of German technology and included parts and blueprints for proximity fuses, anti-aircraft shells, jet planes, and chemical rockets. Now the proximity fuses is the connection. Keep that thought in mind. But nothing the U-234 concealed in its warrants was more surprising than 10 containers filled with 1,200 pounds of uranium oxide, the basic material of atomic bomb. Now, there's a whole book written called Critical Mass by Carter Heidrich that takes off on this tangent of how did Germany come up with 1,200 pounds of uranium oxide? And we won't go there. That's a subject for another story. But suffice it to say that this submarine, at the end of the war, when Germany surrendered, they sent out a message to all of the submarine captains to surrender to the nearest Allied forces. This particular captain decided to surrender to the United States. So he actually took his submarine to the United States. And there were 2 Japanese Army officers on that submarine that committed suicide when they were heading to the United States. Very sweet. And the in Carter's book, he makes the connection that put Oppenheimer up in Virginia at the same time that the submarine was coming in. And several people have speculated about what happened with that uranium oxide. Did it in fact get shipped down to Oak Ridge, get put into the uranium that was being prepared for Livermore? Many people like to think it did. And those proximity fuses are thought to have made their way to Los Alamos and have been beneficial in preparing the fuses that were needed for that implosion bomb. Now, all of that's speculation. You don't know. No one's ever been able to trace it down. They talk about here the difficulty of digging it out of the classified and secret information about what was actually happening back then. But even if none of the submarine's cargo went into the explosive pits, some experts told the U-234 episode is important to explore for what it reveals about the Japanese atomic bomb program, which has long been clouded in ambiguity, even to the point of one theory has that the Japanese actually exploded the atomic bomb in North Korea. And that's another one I want to think about. It's highly speculative. But there was a video made shown on the History Channel where a Japanese individual who said he was a part of that program put forth the idea that they actually did.
Wow.
Whether they did or not, can't
What
be
was the
proven.
date of that submarine surrendering?
May of 45. Yeah, surrender in May of 45. I think it was.
Yeah,
I
that's-
don't get it, Dave. I just get May of 45.
well, it must have been because the surrender was in April, wasn't it?
So it was that.
And that's a pretty quick time for the proximity fuses to make their way to Los
Yes,
Alamos.
yes. Yes.
Because which was it I forget now, the one tested in Alamogordo, was that uranium or plutonium?
No,
Oh, I
it
see.
was the implosion bomb, and that was the reason to test it, was to make sure they could implode. Nobody doubted that the little boy would work. You know, got to do enough of it together to run out. And you brought out some really good thoughts about how fast it is. And if you look at how much actually exploded, how much the little boy had a very small amount of fission that actually took place.
Right.
And that's because of that need to hold that thing together long enough for it to get that chain reaction.
Right.
It's hard to do. But the fact that if you didn't have 32 implosions at one time, you wouldn't get that compression on it to come forward. That's the reason for the test, to make sure that all 32 of them can go off simultaneously.
That's where Oppenheimer thought it will not work.
Right.
But Niedermeyer and his group made it work.
He did, and I believe his name is Kitchikowski.
Yeah, Kistakowski, George Kistakowski. He was a chemist. Or maybe it was George Kistakowski from Harvard, I think. He went up Los Alamos. He was friends with Conan or somebody. I think he was a chemist from Harvard. He was crucial apparently for making that uniform propulsion device work.
It was.
Movie showed somebody trying to make that work on, and never could, and then Oppenheimer brought in a whole team.
I think it was Kistakowski.
Yeah. And the connection between this submarine U-234 and Kitchikowski is what you want to look for, to see if there's anything that he learned from the German technology.
I want to just tell you quickly a little story. There have occurred natural reactors, not recently, but in Central Africa, in Gabon, Central Africa, we now realize that there are 16 sites where there's evidence that 2 billion years ago, there was a natural reactor, uranium fission, that went on, ran for a couple 100,000 years, averaged 100 kilowatts of output. And it was a case where you had uranium deposits. You had water seeping in that geological layer. You had sandstone that would seal that. And apparently, you had a natural reactor run in
those sites, 16 different sites for 100,000 years. And the reason that's known is that in 1972, in France, they did mass spectrometry of uranium hexafluoride samples from that mine in Gabon. And it showed that there was a deficiency of uranium-235 compared to naturally. You see, naturally, now on Earth, the concentration of uranium-235 is 0.72% of natural uranium. They kept consistently finding samples where it was a little smaller. Not a lot, but 7.17%. That led those scientists to start thinking, how could that be? And then they started looking more carefully at different soil samples for those mines. They found that some uranium ore had a U-235 component as low as 0.44%, which is, gee whiz, almost half as much as you now have. Now we understand. You see, the half-life of uranium-238 is 4.5 billion years. The half-life of uranium-235 is shorter, 0.7 billion years. So that's decayed away. But back, you go probably back 2 billion years ago, then uranium-235 made up 3% of natural uranium, not 0.7% now. You go back 2 billion years. Well, 3% is what we use in reactors. Now, when you take uranium ore and you enrich it through one process or another, you bring it up to 3%, maybe 5%, and that's what you put in a nuclear power reactor. Well, that existed naturally 2 billion years ago. And so if you have uranium ore, and if you have water seeping down, when you had a high concentration of uranium ore, you'd have uranium, you'd have a moderator, you'd water, and you'd have a reactor going on. And so that's what happened. And those reactions would run for maybe 100,000 years in the ground in this place. So that did happen. Can't happen anymore because the half-life of uranium-235 is short compared to 238. So its percentage has dropped from 3% down 0.7%. In another billion years, it will be down a lot more. Anyway, I thought that's an interesting story.
You remember we talked about where the bulk of the uranium came from for the Manhattan Project, from the Belgian Congo.
Yeah.
And that the high percentage of the uranium in that ore, in some cases, was as high as 60%, which is extremely high compared to what you normally find today, less than 1% in most of the uranium mines. So some speculated that there may have been some similar situation there.
Right.
In eons ago that caused so much of that uranium to be but I don't know.
Interesting story.
So the center of the earth is very hot. Is that because of nuclear reaction?
Yeah. Not uranium, but
Not uranium.
no, but just radioactive decay of long lived. Yes, partially uranium, but other things.
But it's not reactive.
It's not a fission reaction. It's just radioactive products left over from the formation of the Earth. Yes, that's why the Earth is hot. You're going to pass the test. Okay.